Hi, this is Elias Fofanov, aka Engineer Spock from engineerspock.com. This section is the introductory one. In this section, you'll learn: what is a unit test? What unit test frameworks exist? How to write a unit test in practice? Naming conventions. How to run and debug unit tests. What are the benefits of writing unit tests? Who should write unit tests and when? The oath of a programmer and how it is related to unit testing. Let's get to the section and start with learning the basics of unit testing. In the next lecture, you'll learn what a unit test is. The unit testing concept was introduced somewhere in the 1970s. Decades have passed. Unit tests are still alive. That's because of their great importance in the field of software development. Kent Beck, remember this name if you didn't know it, introduced unit tests in Smalltalk, the first object-oriented language. I don't want to dig the history, so let's get started with a simple definition of a unit test. A unit test is a function which calls another function, unit, and checks the correctness of the outcome from the called function. If the outcome is incorrect, or in other words, unexpected, then the unit test fails. If the outcome is correct or expected, then the unit test passes. Another important definition is the definition of a system under test, or SUT in short. Units are usually contained within classes, so we usually write many unit tests for a single class. Such a class we call SUT, or system under test. In the beginning, I also want to give you a definition of an integration testing, since I want you to understand the difference between these two absolutely different concepts. I like the definition from the book of Roy Osherov, The Art of Unit Testing, with examples in C#. Integration testing is testing a unit of work without having full control over all of it and using one or more of its real dependencies, such as time, network, database, threads, random number generators, and so on. So, the main difference between unit tests and integration tests is that unit tests isolate units they test. Isolate, for example, from working with networks or databases. At the same time, integration tests just take the whole system or whole parts of it and test it as in real life with all the dependencies, such as a database. You'll see special techniques for isolating units further in this course, in the section about test doubles. So, as a result of the difference between unit and integration tests, it becomes apparent that unit tests should run faster and be more reliable. I don't want to look at the properties of unit tests closer right at the beginning, so it's enough for you to understand the difference I described so far. You'll learn more about properties of good unit tests later in this course. Let's talk a little bit about unit testing frameworks. Before jumping right to writing unit tests, I want to say a couple of words about unit testing frameworks. Yes, in the real world, developers write unit tests relying on special unit testing frameworks. Perhaps the most popular frameworks are the following: MS Test, NUnit, and xunit.net. I'm sure there's a bunch of other frameworks, but the intention of this lecture is not to compare different frameworks. The most important thought I want you to understand is that there is little difference between different unit testing frameworks. Yes, all of them have some advantages and disadvantages, What I'm talking about is that once you understand how to write unit tests with any unit testing framework, then you'll be able to write them with any other unit testing framework. It takes 1 or 2 days to grasp all the features of a particular unit testing framework. So, if you have some experience with NUnit and you see in a vacancy the requirement to be familiar with another unit testing framework, don't draw attention to it. You easily can understand any testing framework along the way. So, I chose the NUnit as a unit testing framework to demonstrate examples in the course, and I can explain why. NUnit is one of the oldest .NET unit testing frameworks, and it has all the features required from a good unit testing framework. It is simple to use and it integrates well with different tools, including Visual Studio itself. MS Test is a framework integrated into Visual Studio by default, so to speak. MS Test has the most powerful capabilities related to seamless integration with Visual Studio. But MS Test out of the box doesn't have some must-have features of a good unit testing framework, such as simple parameterized tests, and it also has some drawbacks regarding integration with continuous integration tools. But as I said earlier, don't be bothered by particular frameworks. They are just tools. Tools are important, of course, but unit testing frameworks are very simple to learn, so it doesn't matter what unit testing framework we're going to use throughout the course. It will not have any serious impact. The last framework in the list is the xunit.net. I wouldn't recommend it at all. There is a lack of documentation about this framework, and those pieces of documentation which exist are sometimes very unclear. So I would choose between NUnit and MS Test in the end. Okay, let's go to the next lecture and write the first unit test. And here we are in the Visual Studio 2017. Something can be different in your Visual Studio, but don't worry, we're not going to do anything that you can't do in older versions of Visual Studio. So, look at the Solution Explorer. We have a regular assembly here named Business. It contains some code implementing business logic. Now it has only one class with only one static method inside. Take a look. The method named parsePort takes a string parameter. At first it checks if the argument is in an appropriate format. If it's not, it throws an exception. Otherwise, it takes a substring and parses the number of a serial port. This method represents a chunk of important business logic. We don't know whether it works correctly or not. Let's write a unit test for this method to check if the implementation is correct. Usually, we create a separate unit test project for each project in the solution, the code from which we want to test. For example, in this case, I'll create a separate project for testing the business project. So I'll add a new project and I'll call it business.tests. Take a notice how I named the unit tests project. Usually we name them by starting with the name of a project which we want to test, and then we add a dot and the word tests. To write a unit test, we need to install a unit testing framework. So I'll go to NuGet Package Manager and install the NUnit. For that, I'll go to business.tests, manage NuGet packages, go to Browse tab and search for NUnit. And now I'll install NUnit. Okay. Done. Before writing unit tests, we also need to do the following steps. For running unit tests written with NUnit from within the Visual Studio, we also need to install a special extension named NUnit Test Adapter. Since we're going to use the third major version of NUnit along the course, we need to install the NUnit 3 test adapter. Let's do this. I'll go to Tools and Extensions and Updates. And I'll go to Online tab and type in NUnit. Here it is. After installing is complete, we need to restart the Visual Studio. Let's do this. To test the business project, we need to add a reference to it, since we are going to use types from it. Now I can write a unit test. So for that I'll rename this class to serial port parser tests, and I'll create a testing method which I'll call public void parse port com1 returns 1. And at first I'll call the method we want to test and assert that we're expecting 1 as a result of parsing com1 string literal. In the unit test, I call the method we want to test, passing to it com1 string literal. I know that the correct result is 1, so in the next line I use a special class from the NUnit testing framework named assert. The meaning of this class is pretty obvious from its name. We use it for asserting statements. In this particular case, we assert that the result has to be equal to 1. So, in essence, asserts tell the test runner whether a test has passed or failed. I've written here two variants of the same assertion. The last one is commented out, and it is the old style of writing asserts with NUnit framework. We're going to use the API of the method named that for assertions. There is a special class is with the equal to method is used. Don't worry, we'll talk about it later in this course. In unit tests, we always have an actual result and an expected result. The expected result denotes how we define the correct behavior of a system. Actual result denotes how a system behaves itself in reality. Our task is to compare the expected and actual behaviors. Okay then, we have a unit test, but we also should have a way to run it somehow. How to run a unit test? In Visual Studio we have a special window named Test Explorer. Let's open it. You can open it via menu going to Test Windows Test Explorer. And it says that we need to build the solution. Otherwise, Visual Studio will not be able to discover our unit tests. I'll rebuild. Still nothing. The thing is that we need to mark testing classes and methods by special attributes to make them discoverable. We need to mark classes which contain tests with a special attribute, test fixture. We need to mark testing methods by the test attribute. Let's do this. So I go to our class and I'll mark it by the test fixture attribute. And I'm going to mark our test by the test attribute. I'll rebuild the solution. And now let's open the Test Explorer. Hooray! Now we see our test. Let's click Run all tests. And our test passes. Let's check what will happen if we make the implementation incorrect. I'll change the last index of prefix to 1. And let's rerun the test. Ooh, it fails. You can click on the test and you'll see the details. Why the test failed. I'll turn back the implementation to the correct state. And I'll rerun the test. And it passes. Congratulations! You have written your first unit test. Let's have a brief discussion of naming conventions in the next lecture. It's enough to write a single unit test to talk about the importance of naming conventions. There are no debates regarding naming testing projects and testing classes. They are almost always named in the following style. Name projects as follows. Project under test dot tests. For example, transaction model dot tests. Name classes as follows. Class name under test tests. For example, calculator tests or customer tests. There are several ways of naming testing functions. I can mark out the 3 major different styles. First, the unit test method's name starts with should, describing the overall idea of the testing method. For example, should add 2 numbers. Second, the unit test method's name starts with the name of a unit under test, underscore, and the second part, as in the first style, starts with should. For example, sum underscore should add 2 numbers. And the third is my favorite one. It is the most complex, but I like it because it reveals the intention of the testing method in details. Here it is. The name of a function should consist of 3 parts separated by underscore symbols. You've seen an example of naming in this style when we've been writing the first unit test. I'll just show it again. Here's an example. Parse port underscore com1 underscore returns 1. The name is separated into 3 parts. The first part is the name of a unit of work we're testing. It can be just a name of a function under test or something more abstract, like user login or remove user. User login and remove user are the examples of naming the first part by the so-called use cases. Use cases are the super interesting topic, and I only can recommend a book to read because use cases are totally out of the scope of this course. The second part is the scenario of the testing process. Sometimes we can just write here the arguments passed in the function under test. Sometimes we can write more abstract scenarios like invalid string format or valid login. All in all, this part reflects the conditions under which the unit is going to be tested. And the third one is the expected behavior. There are 3 ways of naming this part, depending on the outcome of the function under test. First, it is named returns value, for example, returns 0 or returns false. Second, it is named changes state or set state, for example, set number to 0. We name it this way when the outcome of a function under test can be observed via its public properties, because the internal state has been changed, and we actually want to validate the correctness of the changes in the test method. Third, it is named calls dependency. For example, calls processing gateway. We name the third part in this way when we validate the correctness of interactions between objects. We will take a closer look at testing interactions between objects later in this course. Okay, now you know the rules of naming so that we can continue our journey to unit testing. Let's briefly look at how to run and debug unit tests in Visual Studio in the next lecture. In this lecture, I want you to get acquainted with the most often used features of Visual Studio regarding unit testing. Here you can see that I've added another unit test which checks if the function under test throws the format exception in the case of the invalid format of the serial port string. I do this with the help of the generic throws method. But in this lecture we're not going to discuss the topic of testing exceptions. I want to demonstrate some features of Visual Studio. You can see that I opened and pinned the Test Explorer window. Let's take a closer look at what this window offers. First of all, we have already used the run all command. It triggers the process of building the whole solution in case the solution has not been built before clicking on this command, and then runs all the discovered tests. Near this command, we have a run command with options. I'll click on that. Here you can run only the failed tests. For example, you can rerun the last running session and other options. You may not understand right now what is code coverage, but we will look at it later in the course. The next feature is called playlists. Right now we can see all the tests in the default playlist named all tests. To create a custom playlist, you can select a bunch of unit tests and add them to a new playlist. I'll create a playlist for a unit test which checks the exceptions. For that, I'll right-click on the test, go to Add to Playlist, and New Playlist. We need to give a name for a playlist. I'll name it Exceptions Checking. And click Save. Now, if I go to Playlist, I see my newly created playlist. I'll click on it. And in the list of unit tests, I see only those which are contained in that playlist. It is sort of a grouping technique. If you want to run only a specific part of unit tests, you can create your own playlist or playlists and run them. If you make a double click on the test, Visual Studio will open the corresponding source file and set your cursor to that test. Using the context menu, you can run tests separately. I'll right-click on any test, and you can see here that I can run it or debug it. If I want to debug the test, I can set a breakpoint and click on that menu item. Let's do this. As you can see, I reached the breakpoint. Now I can debug the test as usual code, step by step, with all the Visual Studio debugging features at hand. I'll stop the debugging. You can also group tests. There is a small icon on the top. Here it is. Here you can choose how to group unit tests, by their namespace, by the class, and many other options. There is another small icon near the grouping one. Here it is. This option turns on or turns off the automatic running of unit tests after builds. I'll turn it on and rebuild the solution. As you can see, after cleaning and rebuilding, all the tests ran immediately after the rebuilding process was completed. Great! Now you have some understanding of what you can do with Visual Studio regarding managing unit tests. You can make your life easier with all these features. Just try them in practice. Okay, let's discuss the benefits of writing unit tests in the next lecture. First of all, let's answer the following question. What is the purpose of the unit test we wrote in the previous lecture? Before writing a unit test, we didn't know if that parsing method worked correctly. With a unit test, we can test if that method works correctly. If someone unintentionally changes the implementation of that parsing method, a unit test will fail, showing us that something is wrong, so we can discover the problem before shipping our software to customers. We now have the documentation which describes the expected correct behavior from the system. As a result, the development team is more productive. Developers have more time to work on new features rather than fixing bugs. Allows to change and refactor existing code without fear to break something silently. Developers are just happier since night calls are over. Complex systems covered by tests are easier to understand. Fewer defects in production. Reduced business costs. Unit tests are much faster than manual testing. Let's pretend that we have a window which uses internally a parsing method. Without a unit test, you need to run a program, go to that window, and click some kind of a button which triggers some logic inside of which that parsing method works. Only after that you'll possibly be able to validate the results. With unit tests, you can just press the shortcut to run all the unit tests and check if the code is correct. Of course, the reality is not so simple as it might seem, but the overall idea is to have a safety net. That safety net is the set of unit tests which we can automatically run and ensure the correctness of the system. A separate benefit which can be marked out is that unit tests are very helpful for continuous integration. Maybe we even can say that unit tests are the core part of the continuous integration process. What is the continuous integration process in essence from the unit testing perspective? Look at the diagram. A developer introduces some changes into the system and writes unit tests. Then he checks in all the changes, including unit tests, into the source control system like TFS or Git. This check-in automatically triggers the process of running all the integration tests and all the unit tests. If all the tests pass, then code changes will finally be committed to source control. Otherwise, a developer sees the errors, fixes them, and checks the code in again. In the next lecture, let's talk about who should write unit tests and when. Many developers think that testers should write tests. Really, why the hell programmers should be bothered by writing any tests? The answer is simple. If you don't write unit tests, don't treat yourself as a professional developer. Developers are responsible for the code they write. If you don't write unit tests, then you're an irresponsible programmer and you should be fired. Sometimes we need testers. I agree with that. but testers are usually responsible for manual testing. Manual testing is when a tester runs your program, clicks on the buttons, and verify by eyes the correctness of the program's behavior. They will not write unit tests. That's your responsibility as a programmer to write unit tests and do it well. Imagine how long it will take to wait for results from a tester to be sure that that function you wrote the last time doesn't crash the whole system. It will take an enormous amount of time. Unit tests are much faster than any testers. Of course, unit tests can't substitute the manual testing. Having unit tests doesn't imply that you don't need any manual testing to be performed. But the thing is that, as I already said, unit tests create a safety net for the developer. Without unit tests, you can't change the code and be sure that you didn't break something. With unit tests, you can easily introduce changes. When should you write unit tests? Of course, you don't have to write unit tests in Hello World applications. You don't have to write unit tests when you write a draft of an application, when you test some kind of idea or something like that. You should write unit tests for any kind of complex applications. To sum up, testers are usually responsible for writing or performing manual tests. Unit tests are much faster than manual tests, so they provide the feedback very quickly. Unit tests create a safety net, enabling fearless introducing of changes. Don't write unit tests for pet projects, which are not much bigger than Hello World app. If you don't write unit tests, you are not a professional. In the next lecture, you'll learn about the responsibilities of a programmer. The problem of programmers' responsibility is very important. Today, programmers do not carry any serious responsibility. For example, a bug in the code controlling the Therac-25 radiation therapy machine was directly responsible for at least 5 patient deaths in the 1980s when it administered excessive quantities of X-rays. Another example, the software error of an MIM-104 Patriot surface-to-air missile system caused its system clock to drift by 1/3 of a second over a period of 100 hours, resulting in failure to locate and intercept an incoming missile. The Iraqi missile impacted in a military compound in Dhahran, Saudi Arabia, killing 28 Americans. Programmers are not responsible for such failures. Doctors who make such mistakes will lose their license. Programmers' working process is not regulated officially in any way. At the end of 2015, Robert Martin, aka Uncle Bob, wrote a blog post where he came out with the programmer's oath. To defend and preserve the honor of the profession of computer programmers, I promise that, to the best of my ability and judgment, I will not produce harmful code. The code that I produce will always be my best work. I will not knowingly allow code that is defective either in behavior or structure to accumulate. I will produce with each release a quick, sure, and repeatable proof that every element of the code works as it should. I will make frequent, small releases so that I do not impede the progress of others. I will fearlessly and relentlessly improve my creations at every opportunity. I will never degrade them. I will do all that I can to keep the productivity of myself and others as high as possible. I will do nothing that decreases that productivity. I will continuously ensure that others can cover for me and that I can cover for them. I will produce estimates that are honest both in magnitude and precision. I will not make promises without certainty. I will never stop learning and improving my craft. At least 3 of these points are strongly related to unit testing and test-driven design. The second, third, and fourth points are not possible to follow without practicing unit testing. Take your time to think about this oath seriously. Are you sure you want to be a programmer? And here is a simple first task for you to solve. We have a class called degree-converter, which exposes 2 public converting methods. The first one takes degrees in Celsius, and the second one takes degrees in Fahrenheit. Your task is to write a couple of simple unit tests for these methods, one for the first one and another one for the second one. If you haven't tried to write unit tests on your own until now, then I strongly encourage you to create your own solution. Add 2 projects, write down this code in one of the projects, and add unit tests in another. So you'll go through the whole process of installing of all the required libraries for writing tests and use all the required types like test fixture and test. You'll feel all the things under your fingertips. If you don't want to calculate anything manually, then I can suggest you to write a test for the toFahrenheit method, which passes in 0 and expects 32 to be returned, and a test for the toCelsius method, which passes in 1 and expects 0 to be returned. Okay, in the next lecture, I'll quickly show you my own solution. And so here is my try. At first, I'll go to Solution Explorer and I'll add a class here. Don't pay too much attention to all the files that you see here. You see them because I record this lecture after the whole course was recorded. So don't be bothered by this. What I do is just add a class here to the tests project, and I'll call it degree converter tests. Okay, I'll make it public, and I'll cover it by the test fixture attribute. Yeah, importing the NUnit.framework namespace. And now I can write the unit tests. So the first test is going to be public void toFahrenheit, because I'm going to test the toFahrenheit method, and I'm going to pass here 0 Celsius, and I expect that 32 is going to be returned, so I write returns 32. What I have to do here, at first I need to create an instance of the system under test, or the degree converter class, in other words. Degree converter, since we're going to test its methods. And I need to act on it, and I'm going to act on the converter by calling toFahrenheit, since we're testing it, and I pass 0 Celsius here. And now I can write the assertion. I want to assert that result should be equal to 32. We're expecting 32 to be returned. And let's write another test right away. I'm going to call it toCelsius, and I'm going to pass 1 when Fahrenheit, and I'm expecting that it's going to be 0 as a result. Yeah, we're going to see 0. Okay, and again I need to instantiate the degree converter, so I'll say new degree converter, and now again double result equals converter dot to Celsius to, for some reason I don't see this method. Seems like this is some kind of a bug. Okay, a bug in IntelliSense. And now I assert that result is going to be equal to 0. Okay, now I'll build the solution. Okay, build succeeded, and I'll go to Test, Windows Test Explorer, and we have here degree converter tests. I'll right click on it and click Run Selected Tests. You can see that I have a problem here. The thing here that the test runner doesn't want to run our tests. And this is because starting from a certain version of Visual Studio, we need also add to each testing project, we need to add the test adapter NuGet package explicitly. So I have here installed NUnit and substitute and other packages, and I also need to install a NUnit test adapter. I need to browse for it. Here it is, and I'll install it. Okay, so don't forget to do this as well. Okay, and if I close it and go here and run selected tests once again, voila, we can see that our tests pass. What means that our production code should work fine. It should work correctly. So this is my simple solution for writing unit tests to test the degree converter. Actually, we can simplify these tests a little bit, but all the refactoring techniques related to unit tests writing are going to be covered in the upcoming sections. Okay, so if you have any questions till now, then please visit the questions dashboard and ask me, and I'll try to give my answer. So if you experience any troubles with running unit tests or writing them or understanding them, please go to the questions dashboard and ask your question. See you in the next lecture. In this section, you learned that a unit test is a function which calls another function, a unit, and checks the correctness of the outcome from the called function. The system under test is an object which contains a unit being tested by a unit test. A particular unit testing framework is not relevant from the perspective of writing valuable unit tests. Unit testing frameworks are very similar to each other. There is a couple of unit test naming templates. My favorite one consists of 3 parts: unit under test, underscore, scenario, underscore, expected outcome. How to run and debug unit tests? Visual Studio detects tests after rebuilding related projects. Any programmer has to write unit tests. That is your responsibility. In the next section, you'll learn the basic features of the NUnit testing framework. Hi, this is Elias Fofanov, aka Engineer Spock from engineerspock.com, and we continue our investigation of unit testing. In this section, you'll learn how to install a unit testing framework and install the runner into Visual Studio, how to write assertions with the new NUnit API, how to write good unit tests with arrange-act-assert triplet, how to run unit tests from the console, to use setup and teardown attributes of NUnit, how to write unit tests with better maintainability parameterizing them, how to group and ignore unit tests, how to calculate code coverage, and what is the importance of code coverage. In the next lecture, you'll learn how to write assertions with the NUnit. The heart of any unit testing framework, from the developer's perspective, is its assertion model. Modern NUnit implements a Fluent constraint-based model of assertions. What does it mean on practice? On practice, we use almost for all the assertions the that method. Here on the slide, you see the signature of a generic that method. That accepts the actual result as the first parameter and the so-called constraint object in the second one. The most important thing here concerns the second parameter. Let's dig into the model of constraints. Constraints are the heart of assertions. I want to demonstrate this system from the practical point of view. I don't want you to cram into your mind all the internal types of the NUnit, so I'll try to simplify things a little bit. With no doubts, at the top level, we have three major logical constraints. Here they are: is, has, and does. These constraints are represented by the correspondingly named classes in the NUnit. The model of constraints is multi-layered. At the next level, we may have, but we are not obliged, other logical constraints. Here they are: all, not, some. This is not a full list, but I give you the most often used. Let's look at several examples of using these constraints. In this lecture, we will look at the examples on slides, and in the next lecture, I'll show you some examples in code, which you can download and play around with it on your machine. Take a look at the all constraint. The all constraint can be invoked both on is and has constraints. The first assertion here checks if all the items in the array contain the letter B. In this case, the constraint expression will be evaluated to true, since all the string literals contain the letter B. This constraint is comprised of two levels, is and all. The second assertion here checks if all the items in the array are greater than 0. In this case, the constraint expression will be evaluated to true, since all the values are greater than 0. This constraint is comprised of two levels, has and all. The not constraint can be invoked both on is and does constraints. Not is the constraint which allows you to build negative logical expressions. These examples are obvious, so I even don't see any reasons to explain the meaning of these code lines in details. The does constraint is most often used for writing assertions on strings. Here are three assert statements. The first one checks if the string ends with the exclamation mark. The second one checks if the string ends with the question mark. And the last one checks if the string contains a substring goodbye. Apparently, the first one returns false, the second true, and the last one false. The has constraint is mostly used with the sum constraint. Here are two examples. The first assertion checks if the array contains any items starting with the BA substring. If there is at least one item satisfying this condition, the expression will return true. In this case, the second item starts with BA, so the expression will be evaluated to true and the test will pass. The second assertion checks if there are any items in the array of doubles, which are equal to 1.0 plus minus 500th. The first item differs from 1 only on 100th, so the expression will be evaluated to true. Also, you can combine logical testing expressions by using compound constraints. Here's an example. Here I use the OR and AND compound constraints. By the way, the NOT constraint is also considered a compound constraint. Okay, so the overall meaning of this lecture is that with the modern NUnit, you can build assertions which resemble expression trees. In the next lecture, I'll skim through all the most common cases of assertions. I added the class character, which represents a character from a game. It can be an elf or an orc, with some amount of health, armor, speed, and so on. It doesn't matter how it is implemented. You can look on your own, just download the source files attached to this course. Let's have a look at the tests. These tests are intended to check the behavior of the character class. The first group of tests shows how you can validate strings in your tests. Don't draw your attention to the name of testing methods. These tests are named like that just because these tests were written for the sake of demonstration different features of an unit, not for the sake of writing real well-written unit tests. So, the first unit test creates a character with the name John, and after that it asserts three things. The first is that the property name actually returns the value which was passed in the constructor. The second checks if the name is not an empty string, and the third one checks if that name contains a substring OHN. Of course, a real unit test wouldn't contain these checks. These checks are here just for the demonstration of unit features. In the real test, I would only leave the first assertion. Let's run this unit test to be sure that it passes. Okay, it passes. The second test demonstrates the feature of ignoring a string case. So, we create a character with uppercase name John and then compare it with the equivalent in lowercase. Here I use in the end the ignore case constraint. Let's run the unit test. And it passes. I'll remove the ignore case constraint and demonstrate that the test will fail. I'll rerun the test. And it fails. I'll fix the test. Rerun it. Great. Let's get to the next group of tests, numerical tests. The first test demonstrates that we can use the is equal to with numeric values. This test creates a character and checks if the default health is equal to 100. Let's run the test. It passes. Also, you can see here two commented out lines, which show how you easily can check the value if it is positive or negative. The next two tests demonstrate that you can use the same API with floating numbers. In these two tests, we just check the correctness of a default speed for a corresponding type of character. I'll run these tests. And they pass. The last test from this group is a tricky one. This test looks very similar to the previous one, but it demonstrates the problem of comparing floating point numbers. Notice that I sum up two floating point numbers to get 1.4 value. Such calculations often reside in the production code, not in the test code, but it doesn't make the example bad. I'll run the test. And it fails. Why? The thing is that 1.4 and the result of summing up 1.1 and 0.3 are different values. There will be a tiny difference between them. If you want to learn more about why this happens, Google for it or look for a good C# course. I'll just say that you should compare floating point numbers with tolerance. I'll comment out the first assertion and uncomment the other two ways of setting a tolerance. The first one sets the tolerance to 0.5 and the second one to 1%. So, if the difference between values which are compared does not exceed these boundaries, values will be treated as equal. Let's run the test. And it passes. The same thing you can use with datetime values. Below you can see the example. The following group of tests demonstrates the API for working with booleans and nulls. The first test shows how you can check a value on null. A character doesn't have a name by default, so this test checks if the name returns null. I'll run the test. And it passes. The next test shows the API for checking boolean values. It checks if the character is dead after getting a huge damage. The last line demonstrates the older but still available NUnit API. And actually, I prefer in such simple cases it more than modern API. So you can use assert is true or assert is false if you like it more. I'll run the test. And it passes. I joined all the assertions in one test to show the features of checking collections. Here you can see that I create a character and fill the collection of weapons by two weapons, a knife and a pistol. After that, you can see how to check if all the items in the collection are not empty. For using this constraint, the values have to implement the IEnumerable interface. String implements IEnumerable so that you can apply this constraint. The next line asserts that the collection contains an item knife. The next line asserts that the collection has exactly two items. The next line asserts that the collection has exactly one item, the value of which ends with TOL. The next line asserts that all the items are unique. And the next line asserts that all the items are ordered in the alphabetical order. After this group of assertions, I create another object and add the same items to its collection of weapons. And the final assertion checks if the two collections are equal. Let's run the test to ensure that it passes. And it passes. The next test demonstrates the API for comparing objects by reference. In this test, I just check if two objects are equal by their reference. For that, I use the sameAs method. Let's run the test. And it passes. The following test demonstrates the API of checking types. Here you can see that I create the object. The actual type of this object is character. In the assertion expression, I check if the actual type is character by using the generic version of the typeOf method. Let's run the test. And it passes. The following test demonstrates how you can check if a value falls within a specified range. Here I check the value of armor. By default, it should be greater than 30 and less than 100. In the commented out line, you can see another way of performing the same check. And by the way, the inRange method includes the lower and upper boundary values. Let's run the test. And it passes. The following test demonstrates the API of checking for exceptions. If a character gets the damage more than 1000, it throws the argument out of range exception. Here you can see two ways of performing the same check. I prefer the generic method throws, passing to it a lambda expression. I'll run the test. And it passes. That's it. As you can see, NUnit provides a very fluent syntax for writing assertions. In most cases, NUnit provides a very intuitive API, which you may just guess how to use it for achieving what you want. I want to stay at one important notion in unit testing, briefly. Remember that almost all the tests comprise of three steps: arrange, act, and assert. Look at this example. Maybe in the previous lecture you've seen simpler tests, but in the real world, tests are usually comprised of three steps. Arrange, where you set up the system under test, then you call one or a couple of methods, and at the last stage you verify the correctness of the behavior by assertions. You may also hear that developers refer to this concept as 2AAA or 3A. In the next lecture, you'll learn how to run tests from the console. Sometimes you need to run tests from a command line. For example, if you're setting up a custom process of continuous integration. In such a case, you may want to create a batch file, the intention of which is to run unit tests from the DLL. So, let's look at how to run unit tests from the console. To run the tests, we need to have a standalone installation of the NUnit framework. I'll show you what I pre-installed before recording this lecture. To download the standalone version, you can visit this site. Since I didn't need the runner with the graphical user interface, I just downloaded the nunit.console. The process of installation is fairly trivial, so there is no need to remove my installation for the sake of showing you the installation process. I have installed NUnit to program files /nunit.org. So, to run the tests, I'll firstly open the Visual Studio command prompt. I already navigated to the folder of NUnit. And to run the tests from a DLL, I can write the following command. This command launches the NUnit console program and passes to it a full path to the assembly which contains our unit tests. I'll press Enter, issuing the command. And all the tests pass. And we see the results here in the console window. The results of running unit tests are saved to the testresult.xml file, by the way. That's how fairly simple you can run unit tests from a command line. There is a fundamental concept related to running unit tests. We need to have a mechanism which allows running some arbitrary code before each test and after each test. Let's look at the code, and I'll show you why do we really need such a feature. We have 4 tests here. In each test, we have the same arrange process. In each test, we create a character object. Of course, there is an unnecessary duplication which leads to unmaintainable tests. We need to simplify things a little bit. I want to refactor out the arrange phase. To do that, I'll introduce a private field. And so I go here and declare the private character field. And now, and I instantiate it right there, and now I can use it in our tests. So character with underscore here and here as well. Okay, so I use our field in our tests now. Done. Let's consider the last 2 tests. Actually, I wouldn't write these 2 tests as separate, but this example demonstrates the problem. Both tests check if the health property returns correct values after some damage was received by a character. Let's run these tests one after another at first. It passes, and another one, and it also passes. They pass. Now let's run all the tests from this class. Oops, one test failed. Let's run the failed test separately. It passes. Let's try again to run all the tests. Oops, one test fails. Why does this happen? The problem here is that all the tests now share the same object we introduced as a class field. Initially, we had a good idea to make our code clearer, but as a result, we have broken the code. NUnit allows to introduce a method which sets up the environment before each test. Let's introduce a setup method. Since we're going to use the setup method, I remove the instantiation, and now I declare the public void method and instantiate the character field right here, covering this method by the setup attribute. Notice that I marked the setup method by a special setup attribute. This attribute tells the NUnit tests runner to call this method right before calling each test method. Let's run all the tests again. All the tests pass. In addition, there is a teardown phase, which is supported by NUnit as well. Imagine that the character class contains some kind of unmanaged resources. In order to avoid memory leaks, we need to dispose the allocated object before running the next unit test. Let's introduce a method which will be called after each call to a unit test. So I'll say public void, and I'll name it teardown, and character calling dispose. We call dispose and assign null to the character field, and cover this method by the teardown attribute. Let's rerun all these tests. And all the tests pass. I want to show you the sequence of executing unit tests. For that, I'll set 2 breakpoints. And I'll debug the unit tests. Setup, teardown, setup, teardown, setup, teardown, setup, teardown. This is how unit test runner works. It calls a method marked by a setup attribute before calling each unit test, and it calls a method marked by the teardown attribute right after calling each test. We have a similar concept of running methods before any other methods on the level of namespaces and assemblies. Look at this code. We have two classes here. One is declared out of any namespaces and another within the business tests namespace. The attribute setUpFixture marks both classes. Each class defines two methods. One is marked by the one-time setup attribute and another marked by the one-time teardown attribute. The test runner will treat the class which is marked by the setup fixture and placed out of any namespaces as the class which sets up the environment for all the tests in the current assembly. The test runner will treat the class which is marked by the setup fixture attribute and placed within a namespace as the class which sets up the environment for the whole namespace. I'll set the breakpoints at the following lines. And I'll debug any test. As you see, we reach these methods. Taking into account the previous lecture, look at the diagram which demonstrates the flow of executing tests by a test runner. Here it is. At first, methods which are adorned by the one-time setup attribute run per assembly or namespace. After that, class after class, the same algorithm will be repeated. A method decorated by the setup method runs, then a test, then a teardown method, and the same cycle again and again. In the end, methods adorned by the one-time teardown attribute will run. Parameterized tests is a very neat feature supported by the NUnit. MS Test supports only complicated data-driven tests out of the box. Look at these two methods. They test the same, just with different values. With Parameterized Test feature, we can refactor them into a single one clean test. So, I'll just comment out these two tests. Okay. And I'll write another test, public void. I'll name it health. Damage returns correct value. And this test will take the damage and expected health. And now we can add test cases by covering by test case attribute. And we pass the values. The first one is going to be damage, and the second one is going to be expected health. So when we pass 100 to damage, the expected health will be 45, and when we pass 80, the expected health is going to be 65. And after that, we need to call damage, act on character, passing damage, and assert that character health is going to be equal to expected health. So this test is going to be run by the test runner twice, once for each test case. Just look at how nice the test is implemented now. With the test case attribute, we can pass arguments into the testing method. In this case, this unit test will be called twice. For the first test case, with 145 passed as arguments, and the second time with 80 and 65 as arguments. The first value will be passed as a damage, and the second value will be passed as the expected health. It is also possible to reuse the test cases by using the special test case source attribute. Here is how we can refactor our example. For that, I need to roll out a separate class, and I'll call it damage source, which is going to inherit the IEnumerable interface. I'll implement it. And we have the getEnumerator method here, and I'll yield returning an array of values which are going to be used as the source for test cases. And here I apply the test case source attribute, passing the type of class that is going to be used as the source of the values for our test cases. This feature allows you to write more complex, the so-called data-driven unit tests. Let's run this unit test and check if it works. All the tests pass. In the next lecture, you'll learn how to group and ignore unit tests. Sometimes you want to group several tests explicitly. For example, you have several tests which run very slow, and you want to separate them into a group, logically. Look at how you can do this. For example, I'll pretend that these two methods run slowly. I'll mark them by a special attribute category. So I'll go here to the method and cover it by the category attribute, passing the name of the category. In this case, this is slow. If you want to see this category in the list of tests, open the Test Explorer and group tests by traits. I need to rebuild the solution. Now you can see in the list the category of long-running tests. The category attribute is applicable at the class level as well. If we mark the whole testing class, all the tests will be in that category. So if I want to do that, I'll just for that copy this line of code and paste it at the class level. All the tests from this class are now in this category. Sometimes you want to ignore a particular test. For example, if a test is temporarily broken. If you want to skip a test, mark it by the ignore attribute. Here's how you can do this. And the reason why you want to ignore this test. Let's rebuild. You can see an icon near the ignored test. The test runner didn't run this test. In the next lecture, you'll learn what is code coverage and how to calculate this metric. I want to say a couple of words about the concept called code coverage. The code coverage is a metric which shows the amount of code which is covered by tests. It reflects that amount in percentages, calculated by dividing the total number of lines on the number of lines which were reached during the process of running unit tests. To run the code coverage analysis, go to Test, Analyze Code Coverage, and click on All Tests. Wait a little bit, and Visual Studio opens a window which shows the results. Here you can see that in our solution roughly 80% of code is covered by unit tests. Expanding the tree, you'll get the statistics on classes and methods. For example, the character class is covered at roughly 70%. If you want to highlight the covered and uncovered code, you can click on the button here. Code coverage is an important metric which reflects the healthiness of the software. But let's take a little step back. and we will return to this topic in the section dedicated to best practices. In this section, let's move to the conclusion. There is an old and one of the simplest tasks given at interviews. I am talking about implementation of a function which takes an integer and returns fizz in case the input is divisible by 3, buzz in case the input is divisible by 5, and FizzBuzz in case the input is divisible by 3 and 5. If the input is neither divisible by 3 nor 5, it returns an empty string. You'd think that this is a toy example. Well, in my opinion it is. However, team leaders who try to hire developers observe that the majority of developers need more than 15 minutes to implement the FizzBuzz algorithm. In this case, the algorithm is actually already implemented. Your task is to cover this algorithm by unit tests. So download the source code of this example and try to write unit tests on your own and compare with my solution in the next lecture. So look at my solution. In this case, we're going to test a single function, which is called ask and reside in the FizzBuzz class. And actually, in this case, we can harness the power of the test case attribute. So I'm going to write a single unit test, but decorated by several test case attributes. So I'm going to define the test fixture here, and it decorates the public class, which is called FizzBuzz tests. We're naming our testing class as usual. And I'm going to name the testing method public void test FizzBuzz. And we're going to take here an expected string and a number that's going to be passed into the FizzBuzz.ask method. So the body of the unit test is going to compare the expected string returned from the FizzBuzz.ask method passing the number. And actually that's it. This is our test. We don't need anything more here except covering our test by test cases. So let's verify the behavior of the ask method. So the first case I want to check is that we expect fizz to be returned when we pass 3. Yep. And I would add another test case just in case, which is going to be 6, and the ask method should return fizz as well. To cover the buzz case, we can pass 5, and we expect here the buzz result. And as well, I would add here, just in case, another instance of the test case attribute passing 10 as the number. And to test the FizzBuzz, I would also add 2 test cases passing, say, 15 and 30. And we expect here the FizzBuzz string literal as a result. And the last test case is actually when the number is not divisible by 3 and is not divisible by 5. So, for example, to test this case, we can add another test case. For example, we expect here the empty string, and we can pass here, for example, 7. And that's it. We covered all the test cases. We don't need to write here many unit tests, so we can write a single one and add several test cases. And now we can run all the tests. And the single test, we have here only one test, but all the test cases, actually it doesn't matter. Either we're going to click here run all on this test or on the class. The runner will run all the test cases. So let's check the results. Let's look at the results. And all the tests pass. So this is my implementation. It's extremely trivial. It's very simple. I hope that you remembered that we could use the test case attribute, so you didn't try to come out with how many 3, 4, 5, 6 or 7 tests instead of writing only one test, covering it by test cases. So this is my solution. Another practical case is to implement parsing of Roman numerals. Let's recall how we count in Roman numerals. I'll just provide a couple of quotes from Wikipedia. The numeric system represented by Roman numerals originated in ancient Rome and remained the usual way of writing numbers throughout Europe well into the late Middle Ages. Numbers in this system are represented by combinations of letters from the Latin alphabet. Roman numerals, as used today, are based on 7 symbols: I, V, X, L, C, D, and M. And there is one peculiarity. The original pattern for Roman numerals used the symbols I, V, and X as simple tally marks. Each marker for one I added a unit value up to 5 V and was then added to V to make the numbers from 6 to 9. So the numerals for 4 I and 9 V I proved problematic. Among other things, they're easily confused with I and VII, 3 and 8, and they were generally replaced with IV, or 1 less than 5, and IX, or 1 less than 10. And this feature of Roman numerals is called subtractive notation. I believe we will have to deal with this case. In short, let's implement the parsing algorithm. We need to implement a function which takes a Roman numeral as a string argument, parses it, and returns a regular Arabic number. In this exercise, I want you to implement the algorithm on your own. Then cover your algorithm by unit tests on your own to prove that your algorithm is correct. And in the next lecture, you'll see my solution. Okay, let's try to implement the algorithm. At first, I would declare a dictionary, so to speak, a map, to map Roman numerals to Arabic, to simplify the way to retrieve Arabic numbers. So for that, I'll declare a private static read-only dictionary of chars and integers, and I'll call it map, and I'll instantiate it right here, and let's fill it by Roman numerals and Arabic numbers. So I is 1, V is 5, L is 50, X equals 10, C equals 100, D equals 500, and M equals 1000. That's all. So, and now let's try to implement the parse algorithm right away. So actually I presume that we can iterate over chars. The string consists of chars, and sum up the Arabic numbers. Let's try. So at first I'll declare an accumulator. I'll call it result, which is equal to 0, and I'll run a for loop from 0 to the length of the input string, and I'll just sum up the Arabic numbers, retrieving them from our map, like this. Everything is simple, and I believe that it should work. Let's cover it by tests to prove that this algorithm is correct. Okay, so I'll go to the Roman numeral tests.cs, and let's create here a class. I'll call it Roman numeral tests, and let's cover it by test fixture attribute as always, and let's declare a method, a unit test, and in this case we're going to use the test case attribute as well. So we will have here the expected outcome and an input string, which I'll call Roman, and the implementation of the test should be trivial, as well as in the FizzBuzz example. So assert are equal expected, and let's call this system under test, the unit under test, parse, passing Roman, and what are the test cases we want to check. Okay, let's start from a very simple one. Test case 1 should be equal, we expect 1 to be returned when we pass I. And for example, we expect 5 when we pass V. Let's run these test cases. And actually these test cases are green. Good. Let's test a compound number, like for example II. It should be equal to 2. Yep. Yeah, I believe it should. So, and it works. Actually, it works. What test cases do we have except these three cases? Yeah, we didn't cover by a test another test case when we have a subtractive notation. For example, let's test the case IV. It should be equal to 4. Okay, let's run it. Ooh, and it fails. It was 6. The result was 6, but expected is 4. Yeah, we need to fix our algorithm. So, actually, to fix the algorithm, we need to detect the subtractive case. And actually, it's pretty simple. So, at first, let's rewrite this. Oh, no. Let's add here a check. So if, at first, in the if statement, let's check the boundaries of the string. So I plus 1 should be less than Roman.length. And if it is subtractive, and to detect if this is a subtractive case, I'll pass here the last two chars, I and Roman I plus 1. That's good. And so actually, if this is not a subtractive case, we're going to add. And if this is a subtractive case, we want to do the same, but with the minus sign. Yep. Yeah. So let's generate this method. And the implementation should be fairly trivial. I'll call these chars as C1 and C2. So we need to compare here these numbers. For that, we are going to retrieve the Arabic numbers, passing these chars. So if map of C1 at C1 is less than map C2, this is going to be a subtractive case. And in such case, we will subtract instead of adding. Okay, so now everything should be okay. Let's run our tests. Win! Yep, everything is green. Okay, so this is my implementation. It should work fine. We covered all the test cases. So if someone will either intentionally change here the implementation for some reason and break the code, we will know about it by running our tests. And they will say what is the problem and where it is. So now we have a working algorithm, correct algorithm, covered by unit tests. Before going further, I want you to try to write several unit tests on your own. You've seen how to write a unit test. In this exercise, I want you to write tests for a simple stack implementation. You can see that I implemented a stack based on list internally. Stack, as you should remember, is basically a collection which implements the so-called LIFO or last in first out. So to add an element you use the push method, and to remove an element you call the pop method. If you want to get the last element without removing it from stack, you can call the pick method. Download the attached source code and try to cover the public API of this class by unit tests on your own. And in the next lecture, you'll see my own solution. So let's try to cover by unit tests our stack class. So at first I'll create here a class covered by test fixture. Sorry, decorated by the test fixture attribute. It's going to be a public class. I'll call it my stack tests. And I would recommend you always to try to start writing unit tests from covering degenerative cases, so the simplest cases. And in this case, I think that one of the most simple cases is when the stack is empty. So I would cover the case when the stack is empty. So the isEmpty property should return true. And for that, let's write a test, which I'm going to name isEmpty underscore. The case is empty stack, and the expected outcome is returns true. Let's create a stack, new my stack of integers, and we can write the assertion here is true, querying the isEmpty property. Yep, the test is done. Let's check if it is green. Let's stick this window here. And yes, the result is green. And the next test I would write, we'll check the count property after pushing one item. The count property should return 1 as a result. Yep, so it's going to be a test named count, since we're testing the count property. The case is push one item, and the expected outcome is returns 1. And for that, we can create a stack, an empty stack, as usual, and then push, let's say 1. And now we can write 1 or 2 assertions. In this case, I actually would write here 2 assertions to check that isEmpty property now returns false. So I recall stack.count, and the isEmpty property should return false. Yep. And let's run this test. And it's green. Okay, what another test I would write? Let's test the pop method. So when the stack is empty, there is a case, yeah? When the stack is empty, we can call the pop method. And it should throw the invalid operation exception. Let's verify this behavior by writing another unit test. And I'm going to call this method pop, since we're testing the pop method. The case is empty stack, and the expected outcome is throws exception. So we can create here a stack, new my stack of integers, and we can write here the assertion right away, throws invalid operation exception, and we pass here a lambda expression calling the pop method. So we wrap the lambda expression by the throws method, like so. And actually the test is done. Let's verify the behavior by running this test. And it's green. Indeed, the my stack throws invalid operation exception in case of calling the pop method when the stack is empty. Actually we need to test the pick method as well. Let's Let's test the pick method by writing another unit test, and I'll call this test pick after pushing two items. Push two items, and it should return a particular item. It should return a head item. So for example, if we have a stack, an empty stack created as usual of integers, and we push 1 and 2, then we can assert that pick should return 2, stack.pick, since 2 was pushed as the last item. Let's verify this. Let's check this behavior. Okay. And it's green. Yes, it's green. And just in case, I think it would be better to write another test, testing the pick method after pushing two items and popping one item, to verify how push and pop work when we have a sequence of calls to push and pop. So at least we need to push two items and pop one. So I'm going to write a test, and I'll call it pick underscore push two items, push two items and pop. It returns head element. And let's create a stack via constructor of integers. Let's push two items, push 1 and 2. Then let's call the pop method, and now we can assert that now pick should return 1. This is the last item. Yeah. Let's run this test. And it's green. Well, what do you think? Did we cover all the cases, all the possible cases? And if we haven't covered all the possible test cases yet, what do you think? Do we really need to add other test cases? You can write on the question dashboard to discuss this problem. I encourage you to think about it. Okay, so this is my implementation. These are my tests for our MyStack implementation. In this section, you learned how to use the new assert that API of NUnit. You learned about constraints, which are used to write assertions. How to write valuable unit tests with AAA triplet. In the first phase, you arrange the SAT, then call the action or unit on the SAT, and in the end, you write the assertion. How to run tests from the console. This can be important to know in case of following continuous integration practices. How to remove duplication by using setup and teardown attributes. How to write parameterized unit tests to remove duplication adhering to the DRY principle, the so-called don't repeat yourself principle. How to ignore and group tests. Grouping can help you to track and organize unit tests to run them in specifically suited bunches. How to calculate test coverage in Visual Studio. Test coverage is an important metric, but high coverage doesn't guarantee that the software works correctly.